So let me get started. Today's class will kind of touch upon the high-level architecture of 5G NG-RAN. So from here onwards, we are kind of go a bit deep into what happens in 5G networks. So far, what I was telling you is about what are all the IMT 2020 requirements for 5G systems, followed by high-level overview of what is the 5G system architecture composing of both RAN and core networks. In the previous class, we have seen various components in core network, how they're kind of deviating from the previous generations of the cellular networks using something called service-based architecture, which is basically thinking every core network function just like the way web server behaves in providing certain services, which clients start fetching it using request response messages or subscribe notify messages. That's what we have seen in the previous class. So today class, I will start talking about what is there in 5G RAN. So things become a bit more complex as you go forwards, but today class is again at the high level, showing you what the 5G RAN does. And then we look at also various layers that are inside 5G RAN, what are all the functionalities. In the following classes, we will start looking bit deep into each and every layer, and we'll talk about some of the critical layers like a physical layer and MAC layer, how they kind of create these frame structures and start providing the resources to the users. So yeah, we'll be spending maybe a week or two discussing these aspects of the 5G RAN. With that, we kind of get to know what are all the things that are there in the 5G systems. Then we can talk some advanced topics. Okay, so this illustration should be familiar with you already. Today class we look at this part. We don't go to this particular split of the NG-RAN. So we look at the NG-RAN in the sense of G node B, more like a traditional base station, except that it is the base station in the context of 5G networks. So that is the kind of thing we look at. Later, when we talk about CRAN, we talk about how we can further disaggregate 5G base stations into multiple components, and we can spread across them at cell sites and also in a remote cloud data centers. So that concept will be covered later, but for today's class, let's look at base stations in a traditional sense of having everything deployed at one location, that is at cell site. So what is NG-RAN? I think I was telling you about this part even earlier. It's basically a new RAN that is defined by 3GPP, providing you both NR radio access and also LTE radio access. So here I'm talking about LTE in the sense of the next generation LTE, which could also can provide you higher data rates and take care of some of the use cases similar to the way NR can behave. So that way 3GPP is kind of looking at two different radio access. One is based on 4G and other one is based on new radio as part of NG-RAN. So yeah, that way you can see that how 3GPP is kind of making operators very comfortable in extending their existing 4G networks as they go towards 5G deployments with the different migration options. So NG-RAN node can either be G node B, that's what I was mentioning, or it could be next generation E node B, which provides you the 4G or enhanced 4G radio access. And these NG-RAN nodes, which could be G node Bs or next generation E node Bs, these are all logical nodes. Again, so 3GPP talks them at the functionality level. So you can use standalone middle boxes, or you can run it as a software on general purpose processors, or you can run it on a cloud if you have kind of computing and guarantees for the latency and whatnot. So you can do any kind of these combinations where these nodes are connected with each other using something called XN interface, and they are connected to the core network using NG interface. I was showing you this also, I think, previous class. Again, we'll come and look at this in the today's class as well, where these nodes can operate at extremely low bandwidth and all the way up to even high bandwidth. So we are talking about using sub 1 gigahertz spectrum bands, so all the way up to going to the millimeter wave, where if you look at up to 6 gig, the channel bandwidth could be up to 100 megahertz. I was talking about this as part of the 5G spectrum bands. Whereas when you go to the millimeter wave, where we are now talking about using the spectrum bands beyond 24 gigahertz, we are yet to see any bands defined between 7 to 24 as of now, where we have the capacity of 400 megahertz even. So, and also one other interesting case is it is a kind of a competition or a kind of good interesting case where the cellular networks also can start operating in standalone mode in unlicensed spectrum bands where you see Wi-Fi access points operate, or even other kind of devices like Zigbee, Bluetooth, and other operators, where the operators can leverage this abundant amount of unlicensed spectrum bands without having to pay any royalty to the regulatory bodies to offer some kind of services, especially the best effort services are the services which user expect at very low tariff, which could be non-real-time kind of things. So these can be offloaded by deploying the 5G base stations in unlicensed spectrum bands, like the way you deploy Wi-Fi access point and unlicensed. That way, 5G, for that matter, even the 4G also, we also have done this kind of research. The coexistence of LTE and Wi-Fi, and even the coexistence of NG-RAN with Wi-Fi, all these are kind of possible. So a lot of interesting deployment options that operators can explore to save their CapEx and OpEx. Let's look at again a few more definitions in the context of NG-RAN. First one is the NG access network. As the name says, here it is a kind of providing a radio access by using NG-RAN, or we can also have non-3GPP access network like Wi-Fi connecting to the 5G core network. So that is called access network. And what is NG-RAN node? As I was mentioning, it could be either G node B or it could be a next generation E node B. So what is G node B? It is a node in RAN that provides both user and control plane protocol terminations towards UV and connected over NG interface to the core. So that way, so if you look at, if I draw this as G node B, on one side it is connecting with 5G core, and other side it is connecting with user. And with user it has something called a U interface, and with the core network it uses NG interface. That's what it basically means. Similar thing even when you take the next generation E node B, that also uses similar kind of interface to talk with 5G core and also with UV. So similarly we have next generation. Okay, it should be actually next generation E node B, it should not be G node B. So if we look at here, yeah, it should be next generation E node B. I think there's a small typo here. And let's look at high level, what are all the different functions that we get in NG-RAN and also in 5G core network. Here you see different components. This is the NG-RAN module. Basically, these are like G node Bs or next generation E node Bs. On the core network, I'm showing you the three main components which are important, and the rest of the component that you have seen, like AUSF, NRF, NEF, AF, and other things, they're kind of backend or kind of an optional things that we use it. So let's look at what NG-RAN is doing and what all these components are doing. So the NG-RAN, it does something called inter-cell radio resource management. So when there are two base stations in the neighborhood of each other, the sharing of the radio resources for cell edge users, that is done by G node B. And other one is the radio resource block control. RB stands for resource blocks. I will talk about maybe next week. what is resource block and how they can be assigned to the users. These are nothing but time frequency resources that are allocated to the users for both uplink and downlink data transfer. Then we have the mobility control, the radio admission control. So unlike Wi-Fi and also in internet, here in cellular networks, we do the admission control. I think those who have studied computer networks, you all know about what admission control means. Before you establish a call or a connection or a flow, you want to make sure that you have adequate resources in the system before you admit that particular session. That's what the admission control is all about. So cellular networks being designed for offering QoS guarantees for voice and other kind of real-time applications, they have this kind of admission control module, which is kind of missing in internet and Wi-Fi because those networks are kind of best effort networks. We also have something called measurement configuration and provisioning, where the base station kind of tells the user equipments when and how frequently they should report the channel state information and information about the neighboring base station, so that the base station can decide whether it has to increase the transfer power or reduce the transfer power, or whether it has to hand over the user to the neighboring base station, or whether it has to change the MCS to higher value or lower value based on the SN or information that is getting from the user. All that is first has to be configured for each and every user. So the measurement granularity has to be conveyed to the user. So that is also done by the base station. And as part of the RB control, somewhat that is closely related to that is the scheduling algorithm. So cellular networks have very interesting set of scheduling algorithms, like all the way from round robin scheduling to very complex priority kind of scheduling one can think of, which is somewhat looks analogous to what the way you do the scheduling in operating systems when you have the different task waiting in the ready queue. Something similar, but it is more complex than even the way you do in the CPU scheduling in operating systems. So we'll talk about the scheduling algorithms separately in the later classes, but that is also taken care by the base station. And interestingly, the base station has to do the scheduling not only for downlink resources when the base station is serving the users, it also has to schedule the resources in the uplink, because in the uplink we have a number of users that are connected with the base station, where the base station kind of regulates who should be transmitting using what resources. That way it can try to avoid collisions when we have multiple users contending for the medium in uplink. So that way base station does both downlink and uplink scheduling. And I will talk about how it indeed does this thing later. And we have seen in the previous class at the high level what these 5G core components are doing. So if you look at very closely, the G-Node B talks with AMF using this interface that is the next generation control plane. So there I was talking about other day using the interface N2. And we have again SMF that is also takes care of the IP address allocation and controlling the PDU sessions. And in the user plane, we have the UPF, which does the mobility anchoring, especially when the user is moving from one base station to other base stations. It is the UPF which kind of buffers the traffic and reroute the traffic to the new base station. And also it does something called PDU session handling. You should make a note of what I mean by PDU session. It is nothing but one or more QoS flows. We have very beautiful QoS model in 5G. So the PDU session is nothing but a set of QoS flows which are given certain QoS guarantees in terms of bandwidth or in terms of loss rate or jitter or other kind of metrics. So these are done by the UPF. And an AMF does something called non-access stratum security. That means when the user is attaching with the network, then we have to make sure that user has right credentials to connect with the network. That is taken care by AMF. And also when you are not using your mobile phone actively, still your base station, your cellular network has to track the user's location at the granularity of something called location area code. So all that is done by the AMF, so that if you are getting any incoming SMS or voice calls or any kind of IP packets, so this AMF does something called a paging, using which it will advertise in the base station that certain user is having certain incoming traffic. That way your handset will start actively connecting to the network to start downloading the data. So that is done by the AMF. So let me show you at bit more detailed level what the NG-RAN nodes do. So first one I already talked about, that is related to the radio resource management, RRM, that is radio resource management. It's all related to establishing these radio barriers, admitting the barriers, connection related issues, and doing the scheduling, all that. That base station does. And it does the compression of the IP header, because with IPv6, we are going to have really huge headers, and you don't want to waste your radio resources in sending these huge headers unnecessarily. We have some IETF RFCs which kind of define how to compress both IPv6 and IPv4 headers, where we can reduce the headers to just 2 to 3 bytes. Because unlike in internet, once the user traffic reaches the base station has to send it to the user over the wireless link, where there's no routing involved. We need IP address only when we have to do the routing, because the base station don't do routing. So again, I am repeating, base station don't do the routing, and the routing is actually done by this guy. Only this guy does the router. This is the router. And the base station doesn't do any routing. So in that case, why we need to really send the IP address as it is? So we can do very interesting compression, lossless compression, so that we can be able to significantly save radio resources in sending these IP headers. It is also done in sensor networks also. You might have heard about something called IPv6 over low power this is called IPv6 over low power wireless network or wireless access networks. So similar concept has been used even in the case of 5G to reduce the overhead of sending IP packets, because there is no routing required here. And it also does the encryption and also integrity protection of the user data, so that your data is securely sent between the base station and the user equipment. Again, I am repeating, this encryption and integrity protection is only between the base station and the user equipment. So make it only the wireless pipe is the one that is encrypted. Same thing even done in Wi-Fi. When you are sending the data only between your smartphone or your laptop to the Wi-Fi access point, the Wi-Fi does the encryption using something called WPA2 or WPA3. If you want to have end-to-end protection, you have to use a TLS using HTTPS. Same thing even true in the case of 5G networks also. And we do something called attachment of the user to the AMF, especially when the user is not clear about which AMF to connect. Then the base station decides about the default AMF for attaching the user. And the routing of the user plane traffic towards the UPFs, where each base station can be connected with multiple UPFs for traffic steering or for load balancing purposes or even for redundancy purposes. And it routes the control plane traffic towards AMF, which internally talks with other backend services to provide whatever the functionality that we expect when you are registering the user or when the users are moving from one base station to other base station and other things. Connection setup and release, that also is done by the base station when you switch on your mobile. Scheduling and transmission of the paging messages. So these messages, this is what I was mentioning, when you are getting any incoming call or SMS or any WhatsApp or other kind of notifications, your handset has to be messaged that you are going to get these messages from the base station or from the core network. So those messages also has to be scheduled over the radio network. So that is done by the base station. And also advertising some system related information where the base station advertises what is its identifier and what kind of power control algorithms or the scheduling algorithm and all sorts of information that base station advertises periodically to the users. So that information is also base station advertises as part of the broadcast messages. This also I talked about measurement and measurement reporting configuration for mobility and scheduling. So this is what I was mentioning where each handset has to be configured to tell what it is observing in terms of the channel quality, neighboring base stations and other things so that the base station can do the appropriate scheduling with the right MCs, and it can also do the handover if the connection quality is going too low and there are neighboring base stations which can be able to nicely connect the users. All that is done by the base station. And also it does something called a transport level packet marking in the uplink. So when the user traffic is going to the core network, the base station does this kind of marking so that the core network can try to differentiate the packets of different flows. Session management, where providing different IP sessions or the PDU sessions, that is also done by the base station. Also network slicing, where we can talk about the slicing at the core network level and also at the RAN level. When you're talking about the RAN level slicing, that means creating virtual base stations where each base station can offer different kind of slices. Then we can have this kind of slicing feature enabled in the base stations. The QoS flow management and mapping to the radio bearer. So even though the QoS flow management is actually taken care by the UPF, after that particular thing is done by the UPF, the base station gets these PDU sessions which compose of one or more QoS flows which are internally mapped with radio bearers that base station is going to establish. RAN sharing, that is also possible in 5G. Dual connectivity, you already have seen how a user equipment can be connected with multiple base stations where it can get a split bearer from one master base station, or it can get two bearers established all the way from core network to the user equipment. One goes over the master node and other goes over the secondary node. And also we can interwork with previous generations of cellular networks at the base station level, where we have seen as part of the dual connectivity how we can take 5G base station and it can split a bearer and send it over 4G base station. So for that we have tighter level of interworking where the traffic first reaches the 5G base station, which internally does the splitting of the traffic across the 5G radio and also sending it over XN interface to the 4G base station so that it internally schedule the resources and start serving the user so that user can get better data rates. So these are all tons of features that we have at the base station. So what I'm showing is the very exhaustive list, and for each of these things a lot of support has to be required in terms of the core network and also from the user equipment by sending or exchanging lots of control messages or the signals that I will talk about later as we go in the lesson. So this slide should be familiar with you. I was showing you this slide earlier too. Now you should be able to look at this slide one more time and see that there are multiple things here. One is we have both 5G base stations and also enhanced 4G base stations. And we also see the interfaces, both NG interface and XN interface, where we use the NG interface to have connection between the base stations and AMF and UPF, and use the XN interface to connect with other base stations. So we have seen this earlier. And now let me show you what these interfaces are actually do. So also make a note that these are point-to-point interfaces or the reference point interfaces, unlike what I was showing in the previous class for 5G core network, where we have SBA, the service-based interfaces in 5G core. Whereas in the RAN and also for connection between base station and with AMF and UPF, we have these point-to-point interfaces. It is also called a reference point architecture. So I will explain you today. So what I mean by these point-to-point interface. So let's look at these interfaces in bit more detail. So try to look at this. One thing that you can notice here is I'm showing you two different protocol stacks. One is for control plane and other one is for user plane. So this is for user plane. And the right hand side one that you see is for the control plane. And this is for NG. So what is the NG interface? NG interface is the one that is between G node Bs this is what I was mentioning, right? If you recall, the NG interface is the one that is between G node Bs and AMF or UPF. And we use this NGU interface for connection between G node B So can somebody tell me where do you use this user plane protocol stack between the G node B2?
UPF.
UPF. Because UPF is the one that handles the user traffic. And the control plane stack that you see on the right hand side, that is between G node B and AMF. Okay. So that should be clear for you. But again, don't confuse here with this arrow. So the arrow that you see here doesn't mean that so this is your G node B and this is your UPF. That is not correct. Okay. So that is not what I mean by the arrow. So what this arrow that you see it here, it is there both in control plane stack and also in the user plane stack is, we have the user plane PDUs. So again, I was mentioning what is PDU earlier too. So we should have noted down by now. What is PDU? PDU is nothing but one or more QoS flows, where a QoS flow is nothing but an IP session with 5 tuple between source, destination on certain port using certain protocol like TCP or UDP. So that's what I mean by PDU session. Okay. So what I'm talking about is we have these PDUs. It is not the session as such. PDU is nothing but protocol data units. We might have heard about something called SDU and PDU. So did you study this part earlier? What is SDU and what is PDU? So how they are related with each other? Can somebody tell me? Anyone knows what is SDU and what is PDU? No? No one knows? PD is nothing but header plus SDU. So at any given layer in the protocol stack, for example, take TCP layer. TCP layer receives packets from higher layer and it puts them in the outgoing buffer. Because TCP being a byte stream, it takes whatever the chunks. Let's say decided MSS is 512 bytes. Then what happens? It takes from this buffer 512 bytes. That is called your SDU. And to that you add your header. That is the TCP header. So the SDU plus header together form the PDU. So the protocol data unit and other one is the service data unit. For our discussion's sake, you can assume that these PDUs are nothing but IP packets. Okay. So these are simply IP packets. So we have these IP packets at the base station. And what is being shown here is when these IP packets are there at the base station, and when the base station is want to talk with the UPF, that's what you see. The base station and UPF are talking with each other. These IP packets, which might have come from the user, will be sent over this particular protocol stack. So these are like a layer 2 and layer 1. It could be any of the layer 1 and layer 2. And this is the IP layer. And this is the UDP layer. We have something called GTP user plane, which stands for GPRS tunneling protocol. So we don't use mobile IP in cellular networks, but we use something that has become very popular and very successful, unlike mobile IP that you might have studied in computer networks. That is called GTP protocol, which stands for GPRS tunneling protocols. As the name says, it was designed even in 2G era to be able to provide mobility when you are having data sessions in 2G networks, not strictly 2G. I'm talking about GPRS, which is an enhancement of 2G networks to provide data services on GSM. There, this particular protocol has been defined. So same thing has been carried forward for 3G networks, later for 4G, even for 5G. 3GP is a kind of going with time and tested protocol for tunneling the user traffic so that user mobility can be handled and user IP address need not be changed because now the user is moving from one base station to other base stations. This is extremely important in the case of handover of the users. So I will come back and explain this more when we discuss about handovers and other thing. But at the high level, you can assume that we use a tunnel between a base station and the UPF using the GTP-U protocol, and inside the tunnel you'll be sending these IP packets. So again, I'm repeating, the base station and UPF establish a tunnel using GTP-U protocol, and inside that GTP-U protocol you send the IP packets that belong to user traffic, let's say. But look at what is happening below GTP-U. What you have here, we have UDP and IP again. Actually, what we are doing is IP in IP. So can somebody tell me where else you use IP in IP when you do internet communication? I'm sure all of you are using IP in IP in your daily life. Can you tell me where else do you use IP in IP except these cellular networks that I'm describing here?
So VPNs?
Yes, you are right. In VPN, we use IP in IP. Similar concept. What we are doing again, see, whenever we say tunnel, so we are talking about IP in IP because all is IP transport I am talking here. So in all these cases, we are talking about IP in IP. But you should not be confused why there are IP packets which are again embedded inside another IP packet. That is for seamless mobility so that these IP packets need not to change their IP address even when the user is moving from one base station to other base station. So that is realized by doing this kind of tunneling. I'll come back on this tunneling and how the handovers are taken care. But so this is the stack that is used to have this tunnel established between the base station and the core network to send these packets inside UDP and IP. So this is in the user plane. So if you look at the couple of points that I'm describing at the bottom of these illustrations, the transport network layer is built on IP transport. The NG interface is built using IP as the transport protocol. In other words, using the IP that is popular in internet. And the NGU provides non-guaranteed delivery of the user plane PDUs between NG RAN node and UPF. So again, try to understand why I'm using the word non-guaranteed delivery of the user plane. So can somebody guess why I'm saying NGU is providing non-guaranteed delivery?
It's UDP.
Yes, you're right. Because we are using UDP, not the TCP below GTPU, there is no guarantee. So if at all you wanted to have more reliability, that has to be taken care above this point. So these are I'm saying as IP packets. So above this IP, it could be again TCP or UDP. So if you have the TCP here, when you are having these user plane PDUs, that TCP layer has to take care of the end-to-end reliability. But between the Gnode B and UPF, anyhow, these GTP tunnel, it doesn't give you any kind of guarantees in delivering these IP packets. So that is the point we have. The reason why this kind of thing is chosen is they don't want to complicate the stuff and have again redundancy or reliability built in at the multiple levels. So let the higher layer TCP takes care if the reliability is really important, or if the higher layer has something called UDP. In that case, anyway, at the GTP tunnel, you don't have to do any kind of guarantees. To make the thing simpler, 3GP has adopted GTP to go over with UDP and IP rather than with TCP and IP. So this is the high-level discussion on how the user plane stack looks like between the Gnode B and UPF, where we are going to talk about NGU as the protocol stack. Let's look at on the right-hand side what is being used in the control plane. This is a kind of very surprising thing when you look at the stacks that use in Wi-Fi and even in internet. In internet, all the time we talk about TCP IP as the stack, whether it is a control plane messages or whether these are the data plane messages. We say that we have a single stack. We use the same stack and the same layers and same protocols for both control messages and also for sending the user messages. But that is not the case in cellular networks. As you see in the NG control plane, the stack is now different. Let's look at only the L1 and L2 look similar to what you've seen in the user plane stack. And then we have L3, that is your IP layer, that is also the same. But then we have in the layer 4, we have stream control transmission protocol. So it is not TCP, it is not UDP. Now we have brought in something, none of the TCP and UDP, which is popular in internet for sending these control messages, which uses something called next generation application protocol as the application layer protocol, which basically composes these application layer control messages and sends them as payload inside SCTP packets. And we have this technical specification 38.420 that basically talks about this particular interface, the next generation application protocol, not interface, the protocol for sending the application layer messages. Because SCTP is also a reliable protocol like TCP, it provides the guarantees or the reliability that you require, something similar to the way you get with the TCP. So that way, I am repeating again, in the user plane, because we are using UDP as the transport protocol, there is no reliable delivery of the messages in the user plane between the Gnode B and UPF. But when you look at the control plane, where we are talking about the communication between base station and the AMF in the core network, we are using SCTP as the transport protocol, which is a reliable transport protocol like TCP. That way, whatever the signaling messages that base station and AMF want to exchange with each other, they will be delivered 100%. So that kind of guarantees we cannot give here in the case of user plane. So let me explain what is SCTP and how it is different from TCP and UDP, and why we are using something that is different from these two in cellular networks. And again, maybe just before I go further, in the last class, if you recall, I was talking about using service-based architecture in the 5G core network, especially for the control plane functions, excluding the UPF. So can somebody recall and tell me what kind of stack I was employing in the previous class? What do you think the protocol stack that we are going to have when you have these 5G core function, control plane function, the 5G core wants to communicate with each other? How do you think the stack will look like there? Is my query clear to you?
There it will be over HTTP, right, sir?
Yes, yes. Yes, it is over HTTP. Okay, that is at the application layer, right? So when we say the word HTTP, we are talking the application layer protocol is the HTTP. Here, if you look at the NG interface, in the user plane, we are not talking about what could be the application layer protocol. It could be your HTTP, or it could be your SMTP, or it could be your DNS, or it could be anything else at the application layer, or it could be your WhatsApp or Facebook. Or anyway, Facebook uses the HTTPS. So these are all different application layer protocol that we have in the user plane. But in the control plane, I am saying that in the layer 5, we are using the next generation application protocol. Similarly, the analogy of this is the HTTP or HTTPS in the application layer. When you talk about the 5G core control plane functions like AMF, SMF, and other things. And what do you think will be the protocols at the bottom of the HTTP?
Sir, HTTP is usually run over TCP, so maybe TCP.
Yeah, you are right.
The
You are right.
IP stack only, sir, it would be.
Yes. Yeah, I think both of you are correct. Yeah. So we are using the TCP IP stack there. And because it is HTTP or HTTPS, you won't be using UDP there. You will be using only TCP. And tomorrow, if you think that TCP is not doing well, you can replace TCP with QUIC as part of HTTP, I think version 3. So that way it is like HTTPS with the TCP, or you can say that HTTP with the QUIC as the transport layer protocol. And that is what up to the transport layer. Below the transport layer, again, it is IP, like IP, the way you see it here, L1, L2, L3, it is some physical layer, some data link layer over the IP layer. That's all we'll be having there. So that way, the stack for the control plane functions in the 5G core is same for all the control plane functions. And the stack there is exactly what we are using in internet when we are talking about web browsers communicating with web servers. Because they're also here using the same stack. Am I right? So that is the stack that I'm talking in the case of 5G core network. But when it comes to the reference point or point-to-point interfaces that we have here in the between the base station and the core network, we have these P2P interfaces where you see two different stacks here. Let's look at what is SCTP and how it is different from TCP and UDP.
Sir, I have a small query.
Oh,
Sir,
yeah.
for the user plane stack, the physical layer will be a radio access, right?
You are right. You are right.
And
But
what will be the data link layer, sir?
so you are talking at the L1 and L2, right?
Sir, yeah.
Yeah, I will show you. I will show you
Okay.
after we are done with this high-level discussion. Yeah.
Okay,
After I
sir.
cover that, I will show you. I will open up the data link layer and show you that data link layer is actually divided into 4 sublayers. In internet, we use like MAC and LLC, right? As the 2 sublayers in the data link layer. Whereas in the case of cellular networks, especially in 4G, we have 4 sublayers inside data link layer. So I will show you after I cover this part. Just hold on.
Okay, sir. Thank you.
So initially, when we are having these PSTN, PSTN is it is also called POTS. plain old telephony system. So if you are having copper-based telephony lines at your homes, so that is called PSTN networks. So there, when you're making calls or when you're receiving the calls, so there's a lot of signaling that happens, similar to the way I'm talking about cellular networks, between your landline phone and with the telephony exchange and with the receiver's landline phone. So there the signaling messages happen over certain protocol stack. There they have something called SS7 as the protocol stack. There we have SS7 messages. Later, because of the popularity of the IP stack in internet, even the telephony systems also started adopting to use IP stack. So what SCTP does, that is Stream Control Transmission Protocol, does is it kind of carries these SS7 messages, which are the signaling messages when you're establishing the call and when you're terminating the call in legacy telephone systems over IP networks. So that is the main objective of SCTP. Okay, I think a small animation glitch. And this again came from IETF as part of RFC 4960. So same thing we are now using in the case of cellular networks, but it is from IETF, the way we have TCP and UDP defined by IETF. And it offers a reliable transport similar to the way you get reliability when you use TCP. And it works at the same layer as that of TCP and UDP. That means it works at layer 4. And using the connectionless data network such as internet at the below layer. And it is message oriented, very similar to the way the UDP is message oriented. Whereas if you take the TCP, it is byte stream oriented. So I want somebody to tell me what you know about these two keywords. One is byte stream oriented and other one is the message oriented. So can somebody tell me what is the distinction between byte stream orientedness that you see in TCP and a message orientedness that you see in UDP? No? Nobody knows? I thought you guys already read about this.
So maybe TCP can fragment the data, so it has to handle at the byte level, and UDP doesn't fragment data.
So TCP maintains something called a buffer. And depending on MSS, it basically takes the bytes from this output buffer or the outgoing buffer and start packaging this with a TCP header and sending it over. And this is like kind of a buffer or the queue that you have at the TCP layer. But if this is for TCP, and if it is for UDP, what happens in the case of UDP? What is message orientedness? Let's say if you have the application header plus payload. So this is the one that is created by our layer 5. And at the layer 4, if you have UDP, so what UDP simply does? It kind of respects the message boundaries that are given by the application layer. So whatever the message that is coming from the application layer, it simply keeps as a payload without doing the chunking or the splitting that TCP does, because TCP does some kind of a byte streamingness. Similar concept is applied even in the case of SCTP. Stream Control Transmission Protocol also is a message-oriented protocol. We take the packets that are coming from the application layer, simply adds its own header and push it down to the IP layer. So that way it is a kind of similar to the UDP when it comes to the message orientedness. But when it comes to the reliability, it is very similar to the way we have the TCP, including the flow control and congestion control. So that way it is a kind of hybrid of both TCP and UDP. The way you say quick UDP I think quick UDP internet connections. Yes, that's what the quick acronym stands for. So quick is also kind of hybrid of both TCP and UDP. So in fact, you can say that some of the principles of SCTP has been borrowed in when Google has initially designed Quick, which further has been made as a standard by IETF. So same principles are there in Quick and SCTP. So I hope this point is clear. So TCP does this kind of splitting of the messages coming from IP from application layer, which both SCTP and UDP doesn't. They simply respect the message boundaries and they send the packet as simply the payloads to the IP layer. Okay, so I think the connection setup of SCTP is like a TCP, where we have three-way handshake, whereas in SCTP we have four-way handshake, including something called cookies, which are related to having secure connections, where SCTP has security built in, whereas both TCP and UDP don't have security built in. They have to rely on using TLS as a protocol for getting security end-to-end. And it has some concept of association instead of connection. In the TCP, we call a TCP connection is established between sender and receiver. Here we say that we have an association made between sender and receiver, where each association can have multiple streams. So make a note of that. Between sender and receiver, I can create one association. Inside that, I can have multiple substreams or streams going on. It is somewhat similar to some multipath TCP. If you have studied about multipath TCP, which also does something of this kind. It has some sublayer, which basically takes the packets from the main TCP layer and creates two pipes over two different links. It could be again on the same network, or it could be also using two different interfaces that are out there with the end devices. So again, multipath TCP is a very generic thing to basically again to improve the connection speeds over multiple NICs or even with a single NIC. So very similar to that, here we have the concept of multiple streams, where we can establish multiple streams as part of a single association. And because we are using these multiple streams, each stream is independent of each other. And if there's any blocking inside one stream, that doesn't affect other stream. So that is not the case with the TCP. TCP is a byte streaming protocol. And if one of the packet is lost or comes out of order, so the TCP does a lot of hangama to be able to retransmit or kind of make sure that packets get delivered in order. Similar thing is done in SCTP at the granularity of the stream level, but not at the association level. That we can have different streams with their own head of the line blocking, but there's no aggregate level head of the line blocking the way you have it in TCP. SCTP separates the reliable transfer of the datagrams from the delivery mechanism. So try to make a note of this point. This separates the reliable transfer of the datagrams from the delivery mechanism. So that is not the case with the TCP. TCP uses called like a three-way handshake to establish a TCP pipe or connection, in which it tries to send the packets in order. And if there are any packets that are lost because of congestion or because of the timeout, start transmitting so that it will be able to get the reliability. So these kind of things have been decoupled in SCTP using these multiple streams. And it also supports multi-homing. Multi-homing is nothing but having multiple NICs with one IP address for each NIC. So where it is possible to have these IP addresses given by different ISPs, so that we can able to make sure that the critical network elements like UPF and AMF can be reachable even if one of the ISP's network is down. In our own campus, so we have two lines coming, one from Railtel and other one is from BSNL, where each one is of 1 Gbps speed. And even if one of the link is failing, still we have a connection up, but at the reduced speed of 1 Gbps. So something of that can be done even here in SCTP when you're talking about the connection between the base station and the AMF, and also with the UPF by having the NICs connected to different ISPs where you can have different IP addresses, and you can do the SCTP connections with all these different IP addresses. And let me explain quickly the comparison between using TCP for getting your HTTP data delivery and using SCTP for HTTP based message delivery. So let's take an example where you wanted to transfer multiple files between sender and receiver, and this illustration is showing you how to get this data if you are using the TCP as the underlying transport protocol. I have a client and server. First, you are making a request to the file. So can somebody tell me what server does after getting a request? A typical web server like IITH web server, which is implemented using Apache. So what do you think this web server does after getting a request from the client?
The first component that is sent by any web server is an index file, and then related components are sent to the client.
Right. So what you are saying, Harinder, is what server will send back. I agree. But before server replies, server does something important. What server does before responding to the client request for getting index.html file?
It establishes the connection.
Okay, so you are right. First, it has to say the request file 0 is the first message that I am showing here. What does it mean? Before you send this request file 0 using HTML, not HTML, HTTP get message, you already have established a TCP pipe. Am I right or wrong?
Right, sir. Right.
So before you see get index.html command on this link, already have established a TCP pipe between client and server. That has already happened.
Okay.
After that only you send get index.html command or a request to the web server. So what web server does after getting the request? No? None of you have implemented web server? You have not done any assignment where you are asked to implement a web server.
So we
Let's
have done web servers, but it's like that, like we are accepting the connection and we are checking what that input is, what the
Let's
client is
assume
asking
that
for, and then we
let's
return.
assume that you are getting a request from hundreds of clients.
Okay.
So what web server does?
It has to do threading, like all of these may not be able to serve on a single thread. So
Yes, you are right. Of course, if you are using Unix or Linux, we say that you fork a child process, or you can also use multi-threading or using pthreads, where the child thread is the one that does the job of responding. Right? Yeah, it could be
yes,
a process or it could be a
yes,
thread.
it was yes.
Okay, send file 0. So what happens after that? Let's take the example of you want to browse IIT Hyderabad homepage where you are making a request to get index.html. So what happens after you get back the index.html here? See here I'm showing the illustration at the HTTP level. I'm not showing you here any TCP messages or so sending this request and getting the response, that means getting the index.html could actually involve sending lots of TCP messages and TCP ACKs between the client and server. So I'm not showing all that, but somehow assume that at the application layer, yes, you got back the index.html. So then what the client does?
Client
So
will
it will
parse
then,
the yes. Continue.
yeah, it will then request for objects that are present in index.html.
Basically does the parsing of the index.html to identify are there any objects that are referred inside it. And again, you start requesting all these objects that are mentioned. It could be again there at IIT Hyderabad website. Sometimes the object that you refer could be pointing to even the third-party websites. In that case, it has to again establish another TCP connection with them and start getting those objects. But in the simple example of all these file 0 to file n are located in IIT Hyderabad web server, you are making a request to get these n on the remaining n files. So then what the child process or child thread does after receiving this request? So my question is, do you use one TCP pipe?
So it depends on like how we implement it. So it can be persistent. In that case, we will be using one TCP pipe, and otherwise it will be having multiple TCP pipes.
Yeah, I think the persistent and using a parallel TCP connections are both are complementary with each other. It's not that they're mutually exclusive.
Right. Right.
Persistent and parallel, we can actually use in a combination where I can create multiple TCP pipes and kept them open so that I can not only receive the current files, I can use the same pipes for getting the future files or the object delivered. The reason why we wanted to make the connection persistent is, why do we make these connections persistent?
To save the time for connection
Yeah,
establishment.
basically the TCP has a three-way handshake. You want to get rid of the time incurred in doing those two round trip times, right?
Right. Right.
And the reason why you want to do this parallel TCP is, why you want to do this parallel?
To get the data as quickly as possible.
Exactly. So we wanted to get the data as quickly as possible, but at the same time, if you are greedy enough and start establishing too many parallel TCP connections, then you may be actually clogging the web servers. That way, many times your browsers put a upper limit of 4 to 6 TCP pipes to a given web server, so that you don't end up eating all the resources in the web server. Okay, that's how typically it is done. So then you start getting in this animation, you see all these files, file 1, 2, 3, so till the file n that you are getting back. So again, I'm showing you the things here at the HTTP level. I'm not showing the things at the TCP level by showing multiple connections or not. At the application layer, you can assume that you made a request for n objects and each of the n objects have been delivered to you in some order here. Let me show you a SCTP header followed by how we can use SCTP to deliver these n+1 objects in the context of web servers. So look at this packet format. We have some common header, which is common for all the streams which are embedded inside one SCTP packet. So we have, as you see here, I have 2 streams, or you can assume that I have n streams, okay, because we are using this dotted line. So yes, I have n streams. And each stream has one chunk. In other words, streams and chunks are the same here, where we are kind of specifying the thing. So there, the main difference between TCP and SCTP here is, so we are sending the data at the granularity of streams, where if you take the analogy of the previous thing, where I want to send a file 1 to file N, I can send using one SCTP connection. So look at how it is dramatically different from how TCP does it. Can TCP do the same thing? Can it send N files over one single TCP pipe?
Yes, yes.
How? Saranjan, tell me how it can send N files over one TCP connection?
Like if you don't close the TCP connection and keep on asking for different GET requests, then
Yes. So,
sequentially those things will come.
but do you think that is different from what I'm showing it here?
Mm, mm, maybe because the format is different, of course, and those HTTP packets are all like different. Like they are not like one is dependent on the other, but in this case, first one is having source port, destination port, other ones do not have.
No, I'm not talking about the header formats and other things. So
Okay.
those details you ignore. So what I'm talking about is you want to get N objects from web server. You have two choices: using TCP to get these N objects and using SCTP to get N objects. And here I'm showing you how I can have one SCTP connection established between client and server or between sender and receiver, where I can have N chunks or N streams that are defined, where I can embed the data of N files, where a part of each of the file can be sent as part of each and every SCTP packet that is exchanged between client and server.
Okay.
And I'm asking, is this same as what TCP does? In other words, if there are N files which you want to send using TCP, how does it send N files?
So in the assignment, what we have done is like we opened a TCP connection and then like consecutively sent in a loop all the GET requests, and we have received in a different thread or maybe in the same loop as well, received the packets that
Or
have come.
is it a ACN assignment?
Yes, yes.
Okay. And what you are saying is you are sending 1, 2, 3, so on N for one TCP pipe. Am I
Yes,
right?
yes, yes.
So is there any better way of doing it in TCP other than that?
Um, Parallel TCP pipes.
Yes.
That
That is second option is you can establish N pipes, right? And you can use one pipe to send each of those N objects.
right.
So that way your assignment is not that efficient, whatever you have done in that assignment,
Right, sir.
right? The internet, current internet, we don't do that old school way of sending the objects. We do actually the second option, where you establish multiple persistent TCP pipes and you start sending one object to other of more than one object in each of the pipes, one after other. That's what you do in TCP. But now look at the second option of the TCP that I'm showing you here of establishing N pipes with what SCTP does when it has to send the same N files. How do you compare this second option that you see it here with what you see it here? And what is the trade-off between these two?
Sir, not sure about this.
So anyone else? Ura, I want to know who else is here. Pradyum, I don't know who is this Pradyum. He never spoken during the class.
Yes, sir.
Ah, So what do you think?
So that pipelining thing is the most efficient.
No, so what I'm asking is, what is the trade-off between these two options? Establishing n pipes and asking each pipe to send one of the objects versus the way you see SCTP does here.
So in N pipes, we have to establish multiple threads of the same for the same connection, I guess.
Yeah, you are right. So that is what you are kind of implying is there's a overhead of establishing n pipes,
Yes.
which you don't have to do
Do
when
an
you are using SCTP, where I can establish only one SCTP pipe and start parallelly sending the data of n files as one of the n chunks in each of the SCTP packet between sender and receiver.
Yes, sir.
Okay, so let's look at the animation again in the context of using SCTP. Look at what is happening finally. All these are happening over one SCTP pipe. And what is the side effect of this? There is no guarantee that the object 1 will be delivered before object n. If it so happens that object n is smaller than object 1, or for whatever the reasons there are lots of losses for object 1 than object n, you may end up actually receiving these objects out of order as well. But that is okay because your HTTP, the HTTP, it doesn't expect delivery of objects in order. So as long as you start getting n objects, it will use them to render to the user using the web browser or whatever it is. So the order is not strictly important because we are talking at the granularity of the objects. Okay, any comments or any questions on this? How we can use SCTP for sending your HTTP messages in internet between the client and server?
So I have just one question. Like, if such is the case that we are sending all the requests together and data for all these requests are coming in a out of order fashion, how is the client or this HTTP or TCP understanding that for which request this packet is coming to me? Like, it's
See
coming
here,
in fragments, right?
so Ranjan, here what I'm talking about is, let's assume that you are using a web browser and in which you have opened multiple tabs. Let's say in one of the tab, you are kind of trying to browse, let's say IIT Hyderabad web server. First, you are making a request to index.html. Then the web server is replied with index.html. Then you started parsing that index.html and found that there are n objects. Some of them could be like images or videos or whatever it is. And now you want to fetch all these n objects and start rendering so that user can start seeing the home page with all different bits and pieces together. So there are two things that I'm showing here. One is your web client is getting these objects from the server, and the second one is once they start reaching, how the web client start rendering them and showing them in the browser. So these two are two different activities. Your HTTP only talks about getting the objects by establishing multiple TCP connections, or if it is SCTP, establishing one pipe and making request over the multiple chunks and start getting the things. But how to render, that is up to the browser's implementation. Different browsers can have different approaches. One browser can say that is, I can start rendering the objects as soon as a given object reaches. Or you can say that I have made the request for object 1 to n. I will start rendering them in the ascending order of the way I made a request. Or in the extreme case, your browser may say that I have made a request for n objects unless I receive all n objects, I don't render the thing. But that is not the case the modern browsers work. They want you to give the feeling of instantly getting the data. So they have lots of tricks which different browsers start applying it to make it as if only one request sent and one response as received. But the behind the scenes, all this happens before you start seeing in your web browser.
Okay, yeah, got it.
Okay, so I am showing you the connection establishment in the case of HTTP and TCP. What you see on the right hand side is the one that you know already, using SYN, SYNAC, and ACK to agree upon the sequence numbers that we use. Can somebody know? Because so what could be the value of X?
Sir, it's a random number, right?
Yes, yes. So the other day I was talking about the pseudo random numbers, right?
Yes.
So we also use the pseudo random numbers to set these sequence numbers. Rather than starting from 0, we start with an arbitrary value to kind of guard against these kind of replay attacks kind of things. Finally, you have this TCP pipe using which you start exchanging the data. Let's look at the handshake in HTTP, which is 4-way. Similar to the SYN, we have something called connection initiation request coming from the client to the server or sender to the receiver. Then what the receiver does is it's kind of acknowledges the request and it generates a cookie, somewhat similar to the cookies that you use in web sessions, which stores some information about the clients. So that next time you are browsing the same website, your metadata is kind of shared with the web server so that you can start getting more relevant pages or the pages that you visited, because that's how we can have statefulness realized in HTTP, because by nature HTTP is a stateless protocol where web server doesn't maintain any state of the client. You make multiple GET requests to IIT Hyderabad web server, it doesn't know that same guy is making multiple requests. So there's no state information. Using the cookies, we kind of maintain state, and you can also use to track the users and understand their browsing behavior or their shopping behavior. That's why the e-commerce websites are kind of very much obsessed with having the cookies. Also nowadays you see your browsers start asking you whether you want to accept all the cookies or whether you want to accept the cookies that are strictly necessary, where some of them track your behavior across the different website that you visit as well. But something similar, but here the cookie is somewhere some hash message that is generated, hash value, and that is the one that is sent back as part of this. So that is sent as a cookie. What the client does is it basically does the echo of the cookie. Whatever the cookie that you are sending, it is echoing back. So that way, by looking at the echoed cookie and checking whether the cookie has been tampered or not using the message integrity check, it verifies that you have established a secure connection between the client and server. So finally, it is a kind of a ACK for the cookie echo that you get from the client to the server. That is the step 4. It is simply an acknowledgement. It is a request. It is a final ACK. And in between, we have a cookie that is exchanged between client and server and echoed back, so that we have a secure connection. This is what I meant to say, where in HTTP we have security built in. That is not the case with the TCP, where you have to use a TLS at a layer above TCP to have a secure connection between client and server. So maybe the last slide for today, which is kind of summarizing what is happening in TCP, UDP, and HTTP in terms of all these different parameters. If you look at reliability, yes, both HTTP and TCP provide reliability, and connection management, yes, like TCP, even HTTP is connection oriented. As you see, we are using 4-way handshake. Transmission point of view, it is somewhat similar to UDP, which is message oriented, where the application layer message boundaries are respected by HTTP. Flow control is there similar to TCP, congestion control is there similar to TCP, and the fault tolerance is something that has been added into SCTP, which is not there with plain TCP and UDP. You take the multipath TCP, yes, that is fault tolerant, where you can tolerate connection losses or the IP address losses and other thing. Where SCTP using multi-homing, you can have multiple IP addresses from multiple ISPs. That way we can have your Gnode BES, your AMF and UPF having multiple links up and active. Data delivery, yes, TCP does the strictly in-order delivery. It is very sensitive to the out-of-order delivery. UDP, yes, it is unordered and it doesn't care about even delivery of the messages. Whereas SCTP, it is partially ordered. That means in a given stream, it is ordered, but across the streams, it is unordered. That way you can have messages or the object delivered out of order. Security, yes, TCP and UDP provide that using TLS, whereas SCTP has some basic security that is built in. As I was mentioning finally, we also have another variant of this, that is QUIC, which is somewhat analogous to SCTP in terms of the feature point of where you can also have multiple substreams inside QUIC, using which we can able to send the data that is belonging to multiple objects, so that we can able to quickly send the data. So the second interface that we have is the XN interface, which is between multiple base stations. And if you look at the illustration, tell me what you notice and how it is same or different from NG interface. Compare this interface with I hope you still remember what I was showing you before I discussed about SCTP. So what do you think, or what you make of here? No? Are you able to follow me? So what I'm asking is a very simple question. This XN interface is same as NG interface, or does it look different from NG interface? Okay, if I want to go back and see NG interface, I'll show you again. Okay, so this is the NG interface. Okay.
Okay, here.
Okay, some animation. I think just bear with me. Oh, so much animation. Oh. Okay. Going back is easy, but coming forward is taking time. Okay. Let's look at this.
So it's looking same kind of.
Okay. What about others? Anyone else wants to comment? How XN interface and NG interface are related, or what are the similarities and differences? Except this, both are the same. In the case of NG, we have NG AP, whereas in the case of XN, it is XN AP. So the rest of the stack is the same. In the case of user plane, it is exactly the same for NG. But here, whatever I was explaining about NGU interface is valid even in the case of XN interface when two base stations are communicating with each other. This is important in the case of handovers, where you have to route the traffic of the user, which have come to the currently associated base station to the new base station to which the user is going to be connected with that. There you have kind of routing or forwarding of the IP packets has to happen using XN interface that is there between two base stations. And if you look at on the right hand side, again we are using the SCTP as a transport layer protocol for signaling between multiple base stations for handover, radio resource management, and even for dual connectivity purposes. Except the case is XN AP is the application layer protocol, because what they wanted to send are having a different headers at the layer 5 compared to what you have seen in the case of NG control plane interface that we have seen for connection between the base station and the AMF. Okay, let me stop it here. And if there are any questions, I will spend another 5 minutes and answer your queries. So we'll talk, I think somebody was asking, I think Ranjita. So I will come back and show you in the following class the stack that is there at the base station and user for the communication between them. So the MAC, RLC, PDCP and HDAP that you see it here, these are the 4 sublayers of the layer 2. So I will talk about this in the following class. Okay, guys. So any queries or any doubts that anybody is having?
Sir, I had a doubt regarding the like how reliability is like taken care in case of SCDP.
It is exactly like the way TCP does the reliability.
Sir, but then like we have multiple streams, so in that case, like for each stream
Yes,
there will be.
you are right. You are right. At the granulata, the each stream you maintain a state and buffers, and you guarantee the things.
Okay, sir.
Yeah. So that is the flow control, congestion control. All of them are as it is. That way, it is more complex than the TCP, as you see clearly, right?
So for each like each stream, the flow control will be different, right? Like it would be taken care differently, or like it will be a common flow control for all the streams.
See, okay, that point I have to check. But see, if you look at here, all these streams are between a pair of source and destination node, are between same sender and receiver, right? So it's not that we are establishing between multiple different receivers. So the reliability are the whatever the in-order delivery and whatever that you have to do, that has to be done at the granularity of the each stream. But what you are asking is about a flow control, right?
Yes, sir.
Okay, so flow control, see, flow control is basically talking about or guaranteeing that the sender is not sending too much data that receiver cannot accept. Because all the streams are terminated at the same end node, so I'm kind of thinking that it is similar for all streams, but I have not checked whether they are kind of independent from each other. I'm expecting because it's the same end node, one stream can learn from the flow control at other stream, but the reliability point of view, yes, we can use the sliding window protocol like stop and go back and select to repeat, using which you can start sending the data. So for any, again, SCTP is a very versatile protocol, even though I'm showing you in the context of cellular networks. So for all these details, I think we have to go too deep into the IETF RFC that is out there. Just check and let me know what you find in the following class.
Yes,
I
sir.
have to check parallelly. So one other document that I wanted to go through, I think you have some break. So this is the 5G system architecture, the technical specification 23.501. So it is, if you look at here, this document. So this is the thing I was trying to explain in the last 2-3 classes. So this document has been updated and it is as latest as September 2021. So it is not release 15 or 16 document. The original 15 and 16 documents that are related to the 5G system architecture have been updated with the new enhancement that have been talked about as part of the release 17 of 3GPP or 5G system. So you can see this document has all those complex details. So it is a 540-page document. So yeah, you don't have to worry too much, but at the high level, so this is the document that explains about the reference architecture and all the different entities that I was explaining, right? That the reference point architecture that you can see it here. And the section 6 of this particular document talks about what each network function does. Like you can see it here, the network function description. So it talks about what each function does. So just go through the document if you want to have more details. Similar to the way I was talking about, you have to use the IETF RFC for SCTP. So this is the authoritative document which is defining all the details related to the 5G system architecture.